Hi, good morning all. Many thanks for joining us. First things first, just a very quick introduction. My name's Chris Given. I'm Strategic Bid Manager here at EA Technology, and I work within our Insights business, where we support businesses with strategic decision making through a range of consultancy and software solutions. We also have Joanne Peacock, who will be delivering this morning's session. Joanne heads up our asset investment management team and has been guiding us through this webinar series over the last, 6 months, is it, Joanne, now?
Yeah, this
Where
is
we've been exploring a range of topics in support of asset health and risk modelling. In this session, we'll be taking a deep dive into asset model data requirements. Previous sessions have covered subjects like the common methodology, defining risk tolerances, defining failure and failure rates, and a whole host of other subjects in relation to asset health and risk modelling. So just the agenda for this session today. We'll be providing a quick recap on asset health and risk methodology components, and look at some of the typical data inputs. Then move on to the data considered in deriving an asset's initial health score. We'll be looking at observed and measured condition data and how this influences asset health scores. Looking at reliability modifier and unit data points. We'll be looking at consequences of failure inputs. And finally, we'll look at some data quality considerations also. Generally, we anticipate about 45 minutes for the main presentation and leave a good opportunity for questions and answers at the end of the session. So, but equally, if you do have questions as we go through the session, if you want to pop them in the chat, or we'll try and pick them up as we go along. Trusting that's okay with you, Joanne. As ever, good stuff.
as ever.
Okay. Trusting that all sounds okay, I'll hand you over to Joanne to get started. Thanks very much.
Okay, thanks, Chris. So probably good evening to most of you. So it's morning where we are, and probably evening where you guys all are. Just a final bit of housekeeping, Chris. You're recording this session, aren't you?
Yes, indeed. Apologies. Yes, I should have mentioned that at the top of the session. Yes, we are recording this today.
Okay. So hopefully that doesn't put anybody off. But yeah, we normally we can provide we provide the slides after the session, and we can provide the recording as well if you require that. Okay, that's good. So we'll move on, and as Chris said, this is all about another one about data. So this is our second sort of data presentation. So slightly different theme this time. So we looked at sort of setting the scene last time, and this time we're going to look in a bit more detail about the different parts of the methodology and filling in data for those different parts. So that's why we've structured it in such a way. So the first part is just scene setting, so asset health and risk methodology. So as ever, we're going to use, if you've been in the previous webinars, you'll have seen this screenshot several times. We tend to roll it out, and it's the general shape of the methodology that we use. And so this is our CBRM methodology, so condition-based risk management methodology, and it also is almost the same, pretty much similar to the common network asset indices methodology, or CNAME methodology, and that's the standard methodology used in Great Britain by the network operators. What you notice, if you've not seen this too much before, is that on the left-hand side of the screen, you've got everything that relates to the asset health and health index. And then on the right-hand side of the screen, you've got things that relate to the consequences of failure. And then those two things come together to make risk. And we've done previous presentations on that. And then the rest is to do with sort of future planning and investments. So we're going to concentrate mostly on these blue boxes today and how we fill those in. So as we go through the session, we're going to use a typical set of data points. So this is the set of data points for the common methodology primary switchgear, and we're going to use this in our example because we've got some data sets and we've looked at just what happens when you apply different levels of data to a particular data set, and that just happens to be primary switchgear. The good thing about common methodology and CBRM is that everything fits into this shape. So it doesn't matter if it's a cable, if it's a building, if it's a transformer or a switchgear, everything fits into this nice generic shape, and everything's called the same names. It has the same terms, and so we can start looking cross asset category. So within common methodology, we've got certain data points. So asset identifier is just the identification of the asset. There will be other, most likely you will have other metadata, so substation name and other information. And then we've got a couple of asset categories. And then from there, we go on and look at the specific bits that fit into those particular boxes that we've shown you. And so the minimum data requirements is the items highlighted. So it's knowing what the asset is, so being able to uniquely identify that asset. And we normally suggest a sort of abstract number for a particular asset rather than a kind of combined key. And that makes it so because it's an arbitrary number, it means that you don't need to change it for any reason. Whereas if you choose a combined key for your assets, then if it's designated to the particular location or voltage and things like that, when things change, or when assets potentially get moved, that can cause particular problems. And we also have issues, we've seen issues where the wrong data, an asset's been replaced and the wrong data is associated with the new asset. So we avoid things like that with a unique identifier. Health index asset category and asset register category are CNAME terms, but what we really mean is a asset category like a high voltage switchgear or high voltage transformer, and it's a health index asset category, so that's quite a broad category. And then for the asset register, that category, that is a subcategory of that. So if you know the asset register category, you'll also know the health index category. And subcategories can be things like the specific voltage of an asset, or it might be like an RMU or a switchgear, and they might all fall within the same overarching asset category. And then the second thing, and then the fourth thing I should say that we require is the age. So that's the absolute bare minimum just to get a result. Now, on this particular slide, I've also got, because it's primary switchgear, I've also got replace moving portion in there. And the reason for that is because I want to go on and talk about the actual setting an expected life for an asset. And replace moving portion just fits into that. It's not an essential data point. You can get away with not having that, and you'll pick up a default for the asset register category in that case. So just moving on to our current health score. So this is the general setup of the way that the health score is connected together. So you can see that although we have the generic shape with the things down the left-hand side, it's actually slightly more, it's actually slightly different to that. So the current health score is an initial health score multiplied by a modifier multiplied by a reliability modifier, a health score modifier and a reliability modifier. And so what this tells us is that once you have a health score modifier, an initial health score, you need to calculate that for each asset, and you'll do that using the age. But health score modifiers and reliability modifiers can be set to default values, and the neutral position of a default value is 1. So obviously, if you substitute reliability and health score modifiers by 1s, you will just get the value of the initial health score. And so by using this mechanism, it means that as long as we've got an initial health score, we can create a result for every asset that we've got. just using the age and the category. So that's quite important. So it's quite a low base that we're looking at, and actually common methodology is designed, the way that particular methodology was designed is for all network operators in the UK as a sort of minimum standard. And so that means that they really thought about who had what data, in what shape was that data, and what do we need, what's the minimum amount of data we need to tell us the most about the condition of the asset. So there's a lot of thinking that's gone into that, and there's a lot of debate and, dare I say, arguments in terms of what went into that methodology. And so that's why it's really important that we sort of start from there as a standard, and it's the closest thing we've got to a standard. So moving on and looking at that initial health score in a bit more detail. So here we're going to look at the age, location and duty factors. So all of those 3 boxes go into the initial health score. And the initial health score itself, so again, I've drawn this out. So that's made up of these sort of, when you see these sort of darker sort of grey boxes, these are actual inputs from asset data. So if you imagine a big list of asset data, this is what we need. The lighter blue boxes, and actually the darker one, are calculations which are specified by the methodology. And then this red box is what we call calibration data. And this calibration data is really important because it tells us sort of a baseline. So for this switchgear in this case, we would look at the different asset register categories and whether there has been a moving portion replaced or not. So that's the other aspect that's looked at. And then for each unique combination of that, we've identified an expected life or normal expected life. And this isn't the point to the end of life. This is actually to a point of a health score of 5.5. So if you imagine a health score scale of 0.5 to 10, where 0.5 is a new asset and 10 is a very poor condition asset, then 5.5 is the point at which we're just starting to be increasing in the probability of failure of that particular asset, and it's part way up that probability of failure curve. And so it's a sort of, another way of looking at it might be your sort of economic life of an asset, or it might be the life which has been suggested, or the expected life suggested by the equipment manufacturer. But that's what we're trying to capture in the normal expected life. And I actually can't remember what they are for switchgear, but they're around about 40 to 60 years for these kinds of assets. So different assets have different expected lives. But the thing about these calibration values is that obviously using CNAME, which is publicly available, you can have a look and see what we think in the UK. But overseas, especially Australia, New Zealand, etc., your assets are going to be different. They're going to be at different voltages, different operating conditions. And so this is the point where you can really engage your engineers and say, well, what would we expect our assets, how long would we expect our assets to take to get from a brand new to a health score of 5.5? And that's clearly a discussion that obviously we have when we implement these kinds of solutions for different customers. So there's a real engineering sort of judgment there. If you haven't got, a wealth of engineers, which you might not have if you are sort of in an industrial setting, then common methodology or other reference methodologies, they're a good starting point for that. And so all we need to populate the initial health score is the age and the asset category. So it's quite a low base in terms of the asset data. And I just put the algorithm on there as well. So in terms of the age, so we use that to create the initial health score. So I've mentioned that. But the other thing that we do with the age is we use it to calculate the aging rate. So we create a theoretical asset initial health score, based on the age and the location and the duty. But then when we've added all the information together to create the current health index, we then look back and see how long it's taken for the asset to go from its new position to where it currently is. And then we use that to create a second aging constant. And it's that second aging constant we use to predict our assets into the future. So you find that depending on the different assets, the different situations, some assets will age more quickly than other assets. So if you've got two assets at a HI7, in 5 years' time, one might be a HI9 and one might be a sort of 7.6, just depending on how quickly those assets are aging. So that age is used to calculate that aging rate and therefore the future health score. In terms of population of that data, it's clearly ideal if you know something directly related to that asset. So the date of manufacture, the date of installation, those dates are all used. It might be a combination of those dates depending on what you've got populated. If you haven't got that information, so customers of ours have used things like the age of the substation or the age of the circuit, and if that's not available, then sometimes we've guessed dates for particular assets, so approximate vintages. So it's less than ideal, but it does give us a starting point. So customers generally know which are their older parts of the network, which are the newer parts, so it's not ideal, but it's better than nothing, and it's good that we can start from at least something. So that's how we would suggest you populate the asset age. And then just by populating the asset age, so I've borrowed this slide from the last data presentation, but what you'll end up with is essentially an age-based profile, and it'll look something like this. So we have 3,000 assets in our population, and if you take the health scores and just categorize them into 0 to 1, 1 to 2, etc., then this is the sort of shape that you will get if you use that age-based profile. It's important to say at this point that we actually cap our age-based profile at a 5.5, and the reason we do that is because we say the methodologies have this constraint that we say that we won't condemn an asset, that is, put it into a value of HI sort of 8 to 9 or above, without specific information to tell us that that asset is in poor condition. And there might be exceptions to this. So this is generally for most assets. It might be slightly different where we're talking about assets like service cables, rising mains, and other things where you just simply don't have any condition information and it's just not practical to gather any condition information. But in general, for most assets, the 5.5 limit is pretty fixed. And so that's why that bucket, that 5 to 6, that contains all of those assets which are stopped because they don't have the condition information. So as you might expect, we're looking at about 50 unique health scores in that case. So then if we move on and look at duty and location information. So these data points are common across the common methodology. We use them in all asset classes. For some assets, those data points aren't especially relevant. So, for example, cables, distance from coast doesn't really matter. And in fact, the location ones don't matter so much. But in that case, we've kept the generic shape of the methodology and they just get defaulted to a value of 1. So they don't have any impact because location and duty are a multiplier, but they are there to keep the general shape. And that just means that when you're looking at a cross-asset report, you can see how many assets are at that default position. Distance from coast is useful for us because we're an island nation, and obviously lots of assets are closer to the coast and therefore impacted by sort of salt spray and the atmosphere that's got salt in it, and that does have an impact on how most assets age, but not every asset. So for example, wood poles that we have, again, a lot of, aren't really impacted by that. But the calibration of the models will set accordingly with with the different asset types. So that's how we can control that. And again, altitude and corrosion category, which I'll talk about a little bit more as well. Obviously, these are UK centric, based on data which is almost readily available. As soon as you start moving away from the UK and you're starting to look at areas that have got different environments, then you want to be picking up different data points potentially for those location attributes. Duty is workload. So in this case, we're looking at the number of operations, switchgear operations. So we'll come back to that in a second. So just a little bit more about location. So in the location, so like I say, we've got these three different attributes. We've also got indoor or outdoor. So in the UK, some of our assets are indoors, and so they're not subject to the same kinds of environmental conditions as the outdoor assets are. So we generally take a decision to reduce the impact of the location significantly if an asset is based indoors, and we use a generic shape for all of the assets. So the other thing you'll notice on here, so the two maps on here are corrosion maps. So the one which is in the shape of the UK, so this is where our corrosion comes from, and this is produced by an organisation called the Galvanisers Association, which really looks at galvanising, particularly on things like steel towers and the impact of corrosion on paintwork. It's clearly UK specific. That data is not available anywhere else, as far as I'm aware. The darker elements are the most corrosive elements, and then the lighter ones are the least corrosive. And corrosion has been they've gone out and they've done lots of measurements, and we've got 10 kilometres square, so we've got quite a rich data set that we can pull from there, and it's quite easy to populate that for every asset in the UK, or certainly in mainland Britain and Ireland, because we've got that data set there. I was doing a bit of Googling as I was putting this presentation together, and I've come up with the bottom one, which is one of the states. There is a corrosion map, but as you can see, it's extremely broad. But wherever you are, which is most likely sort of Australia, New Zealand, sort of east of where we are, you can see that there are, there's different data sets. So you can't just pick up, for example, the common methodology and use those particular factors. You'd really need to look at what data was available in your area and how you can match that into a set of factors or multipliers for your models. So that's location. Duty is based on the asset type. So obviously I've mentioned the number of operations for the switchgear assets. These are all defaulted. So the default standard is like I say, that's 1, and duty is a multiplier. So for switchgear, we generally use number of operations, and this is quite chunked up. We're not after, or certainly common methodology doesn't use exact numbers, but it looks at, it's actually a low to medium and then a high. But you could look at using a low, medium, high, or whatever else works based on whatever data that you've got. Tap changes use tapping operations. Transformers use utilisation, as do cables, and then we also look at the voltages. And then there's some assets that it's just impractical, or it doesn't make sense to have any specific duty. So, for example, a wood pole doesn't have any duty, or a tower, or a fitting. So those are just set as default, as standard. And so when I was preparing this, I prepared some data and looked at the impact of duty and location just on these on primary switchgear, and I've come up with this sort of chart. And so you can see all the different data points. So we've got distance from coast. And so I've got a default. So this is what happens when you have no data at all, or the minimum data. And so I've got default old, and then I've also got a default young. And then I've sort of looked at what's the best case scenario for an asset and what's the worst case scenario. And again, for old and young assets. And so within this chart, we've got, so distance from coast. So the worst is that it's very close to the coast. So I've got 1 kilometre there, and you can see the factors appear here. So factors are things that hover around 1. So you can see that if there's no data, it's just a 1. If it's best, it's a value below 1. So these are the common methodology values. And so that will make the initial health better. Or if it's worse, it's a higher factor. So that will multiply, it will be used as a multiplier, and that will make the ultimate initial health score worse. And so I've done that for distance from coast, altitudes, corrosion. I thought it was unfair to compare indoor and outdoor assets, so I've set them all to be outdoor. And then you can see the expected life, the normal expected life, so this is what we set in the calibration values, is 55 years. That's for across the board. The actual lives I've chosen have been 40 years for the old assets and 5 years for the young assets. And so we've got aging rates and expected lives, which are the calculated expected lives for those particular assets. And so we can see the impact on the initial health score. So for the assets in a default location, that's coming out at 2.86 for that 40-year asset. So that's moving along its trajectory, but it's not at the point where we're concerned about it. But actually getting some of this location information, because you don't have to go out and collect it. It's data that's normally available via a bit of research or a bit of knowledge or using GIS systems. It's usually quite easy to fill in the location data. The duty might be a bit more difficult. Best case scenario is 2.4 and the worst case is 5.5. So you can see how just by having this basic data can influence exactly your starting position for your assets quite significantly. When it comes to the younger assets, there's not a lot of difference really. So the message here really is that if you're going to then start collecting data, just go for your older assets first. I know that's probably common sense, but there's quite a big difference between 5.5 and 2.4 as a starting point. And obviously, as the assets get older, they will start accelerating in their condition more rapidly. So go for those first. And then when you add in this particular data, your condition and so your location data and your duty data, then you start to get a much bigger range of values. And the graph doesn't really show the sensitivity of data, but now instead of having those 50 different values, we've now got over 200 different values for our initial health scores. And again, they're capped at that 5.5. So you'd really want to sort of prioritise some of these worse location, higher duty assets potentially for inspection if you haven't got inspection data for them. So that's what the graph looks like at that point. So now we'll move on and look at observed and measured conditions. So these all fall into this box called the health score modifier, shown there. And actually, this is the sort of the setup. So for each observed and measured condition, we've got a cap, a collar, and a factor. So we've met factors already. They're things that hover around 1, and we'll meet caps and collars in a second. On the right-hand side, you've got oil analysis. So oil test modifier, which is specific. I mean, these are specific to transformers or higher voltage transformers. So oil test modifier is your acidity breakdown strength and moisture. Your DGA is your component gases, and then you've got your furforaldehyde, and they're classed as slightly separate items, and each one of those again has a factor, a cap and a collar. And so just to put some definitions on these, so we've met factors already, and what they do. In terms of combining factors, so you'll see in the methodology that lots of things produce factors, caps and collars. So but the factors are the most complicated one in terms of combining factors to create overall factors or overall multipliers. And the way that that's generally done is that for the ones that are greater than 1, so factors greater than 1, we take the highest one, and then for the remaining factors up to a defined number of them, we take a proportion of those factors. There is an explanation in CNAME if you want to sort of have a look at that, but it can be a little bit confusing. So I've really tried to make just a one-liner that tries to explain exactly how those are combined. So for caps, these are used quite rarely. So these set a maximum health score. And it's, I put an example there of tower painting where it's capped at 6.4. And that's because for a tower, we create 3 health indices, one for the steelwork, one for the paintwork, and one for the foundation. And so for the paintwork one, there's a single observed condition point there, which is the paintwork condition. And so we cap that at 6.4 because we don't want that health to get too high just based on the condition of the paintwork itself. So you wouldn't replace a steel tower because the paint is poor. You would replace the paint system. You would, strip it back and do what you need to do there. So caps are used, but not very often. And when we combine them, we just take the minimum value of the caps. Collars are used quite extensively. So these do the opposite of caps, so they set the minimum health score values. They ensure that, because when we start with a initial health score and we have these multipliers, if you have a very low health score, like we saw in those young assets, your multipliers would have to get really high before your health score actually was elevated to a point of 7 or 8 where they'd be on the radar for you doing something about them. So the collars really are to pick up poor condition of young assets. If they're older assets, they'll get there anyway with the factors and those multipliers, but if they're young, they probably won't. So these are things that you need to do something about, and we combine those by taking the maximum of the collars, the highest of the collar values. So in terms of observed conditions, so every asset class has usually up to 10 observed conditions, and these data points are the things that you go out and collect on inspection. And so for primary switchgear, I've put those in red on the screen. So different values, and these different data points also have different, what we call calibration values, as I've mentioned, so different associated factors, caps and collars. And so you can look at those factors, caps and collars and see which are the most, or which are considered within CNAME as the most important or significant data points to collect. When you're collecting condition data, so some suggestions here. Really, every time you go to site is an opportunity to collect the observed conditions. You're not taking the assets out of service. You can usually just collect those whenever you go to site. And usually in the UK, certainly for plant assets, 12-month inspection cycles are the norm. It's a lot longer for things like overhead lines, can be up to sort of 5 or even 6 years for some asset classes. That might be different depending on where you are. We do suggest using digital systems. I'm sure you're probably thinking this is teaching an old dog new tricks. We still get sort of paper records and things like that. It is more helpful if it is a digital record, but obviously paper records can also be digitized as well. But if you're sort of starting from scratch, a digital method is the way forward. And then the other things we would suggest is, if you're designing your inspection, try and go for a set of allowable answers. So, for example, switchgear external condition, which we've just met in the previously, that has 4 discernible allowable values. So no deterioration, superficial minor deterioration, some deterioration, and substantial deterioration. And if you look in CNAME, what they've done is they've provided a description of what they mean by no deterioration or substantial minor, and they've also produced, which isn't publicly available but it will be published on what is our ENA website shortly. It is written, they've actually done a photographic guide for each of the condition points as well. So they said, for this particular type of switchgear, this is what a photo of superficial looks like, or some deterioration. And so that helps when inspectors go to site and they can, obviously match the picture. I know that sounds a bit basic and it's a bit more complicated than that. The jury's out on whether you should provide previous inspections to a new inspection, to somebody going out into the field. I was having a discussion with one of our network operators and having that debate, and his view was, well, they could just copy the last inspection. If they had the date, if they saw the last inspection there, they could just copy that. But then there's also a view that if they can do the inspection first and then see the previous inspection, you might get better consistency. So I don't have an exact answer on that one, but it's an interesting thought in terms of how do we tap into inspectors' sort of psyche to get those results, a better quality and more consistent overall. And then measured conditions are set up in exactly the same way. So you have, again, up to 10 measured conditions. And for the primary switchgear, these are partial discharge, which is on the left-hand side, and then some other tests, IR tests, oil test, temperature readings, trip tests. These are a little bit slightly different. So you'd have to determine the practicality of going out and testing and doing each of those tests. Certainly in the UK, we do a lot of trip testing, and we do a lot of partial discharge, but we do relatively few IR tests and oil tests. They don't often come up in the data sets because they're not often collected by all the network operators. It's not always practical. So even though you see a data point in CNAME, not every network operator will go and collect every single data point. It's not a mandatory condition that they need to do that. There is an assessment of the practicality. So don't think they're collecting, everyone's collecting 6 data points every year for, switchgear. They're not. It's based on what is practical to collect. Observed conditions are different because they're visual, but measured are usually, there's usually some practical element to that. For cables, so this is a slight exception. We collect fault records and records of losses of gas and oil. So from pumping records, we collect that kind of information is collected, and that's used within the measured condition modifiers. The reason for that is because there's, you don't dig cables up to look at the condition generally. You might take cables out of service and learn something about those, but usually it's impractical to collect the observed conditions. So it's a case of trying to just have something that moves that health along and something practical that you can draw upon. There are also some, so for switchgear, so I've put a couple of examples here where you might sort of choose one test over another. So trip tests are more likely to occur with assets with low numbers of operations because they're more likely to stick. Assets that have got a high number of operations, if you're doing trip tests, you might prioritise the low operations assets. It's a suggestion. And then partial discharge. So we've done previously quite a bit of analysis on partial discharge, and that can occur at any age on any asset. But it's more likely to occur on higher duty older assets, more likely, but we do see it everywhere. But our suggestion on this, potentially, if you're looking for which assets, is target the assets. If you're interested in making sure that you're trying to get as much, avoiding unplanned outages, then if your observed condition is telling you that that asset is in very poor condition and it's at a point where you're going to do something with it anyway, you could confirm that with a kind of PD test and see whether it's got PD as well, or you could do another asset which has got good observed conditions, and potentially if you find PD on that, you've got another asset I know that you need to worry about. But there's a certain practicality there that look at your assets that you don't know something about. It would be our suggestion. And as I mentioned, those caps, collars, factors are indicative of the importance of each data point. So once you've done that, and when we've added that into our 3,000 asset data set, we get a much richer, more diverse set of health scores coming through. So in this particular slide, what we've done is take on the age based, or age and location, we've removed the 5.5 cap, and the reason for this is just to allow those assets to extend beyond 5.5 so that we can really compare what an age-based profile looks like compared to a condition-based. And we can really see that there's a big spike up at that 5.5. And so these are assets that are old, but they're also in good condition. And so if we just look at our replacements based on age, you know, we've got all these blue ones over on the right hand side in these higher health score buckets that we'd be doing something with, when actually, you know, with a bit of inspection or a little bit of data, we know that they're in good condition and we don't need to do so much with those at the minute. Yeah. So we'll now move on. I realise I've got quite a few slides left, and I'm running short of time. So we'll move on and do reliability and units. So reliability, these are not really related, but I bucketed them up just for completeness. So reliability comes in at the health score, and then the units comes in at the probability of failure as a multiplier. So these are the elements on here. So we're looking for a factor, a collar, and a number of units. The number of units is universal, and I'll talk about that in a second. So reliability collars, so common methodology uses a factor and a collar, and reliability is really a catch-all bucket for everything else that you haven't to do with condition that you haven't previously picked up. So you set a factor and you set a collar, and in GB in Great Britain, if they use this mechanism, they also have to justify exactly why they've used that mechanism and why that's not picked up in the condition or the location or anything else. But they can use that as a bucket. For CBRM, what we try and do is really identify, is it a make and manufacturer type issue? So is it a bad batch of switchgear for a particular manufacturer, or is it, you know, something else that's relating to that asset? So we try and do that and use the calibration values to set the reliability in that way. But whichever way you do it, it's just that catch-all bucket. Okay. Probability of failure. I've got a whole webinar on this slide, which you might have seen. But what I've done, the addition I've made is just adding in this units right at the end. So for linear assets, the probability of failure is always multiplied by the length of the cable or the conductor. For assets which are not linear, that is effectively a value of 1, so it doesn't make any difference. But in the models that we build, we always put units in for every single asset, and the reason for that is because it allows us to have these really generic structures for reporting, so it's always included as part of the reporting. But also, when we've done some investment modelling and things, we can do things like replace one and put two in, for example. So we can use it for that mechanism. And as we're moving forward and we're just starting to think about what assets will be in our future price control, we're starting to think about including in CNAME version 3 things like service cables and batteries and cutouts and some assets which are very high volume but low data. And so we may not model these on an individual asset basis. They may be done in groups. So groups of assets of particular types. And in that case, we know we've got certain volumes of them. So by keeping our models the same shape, it means that we can associate those particular volumes and always include them with what we do. So couple data collection for reliability. So reliability is populated by exceptions. So this is where we talk to your engineers, we go through what are the issues that you're having, have we captured those elsewhere. It can be used for things like policy decisions and things. So if you know that you need to remove a particular undesirable type of asset for a particular reason, then yes. So I've just seen a pop-up saying risk equals cost times consequence of failure times probability. Yes. Then yeah, we can remove undesirable assets or bring those to the top of the pile. If it's not populated, it will just be a default value of 1. And then the units is again set to a default value of 1 for most assets. You need to think carefully about your linear assets. I think probably overhead lines, there's probably an approximate default that you can set for those. Cables are usually a bit more tricky because you tend to chop those up into smaller or bigger sections. So consequences. Sorry, I've just seen another thing pop up. Are we considering consequences? We are, and we will do consequences now and really quickly as well. So consequences of failure is everything on this right hand side of the right hand box. And the way that the consequences work is different to the health. So for every asset category or asset register category, we start with a reference cost of failure. So this is the average cost for replacing an asset, the average customers affected if the asset is not available anymore. It's the average sort of safety implications based on your safety records or environment. So we start with an average, and then we have a criticality factor, and we multiply the two together. So it's the reference times the criticality factor, and the criticality factor is specific to every asset category. No, it's the criticality is specific to every asset. And that means that just by applying the calibration, we can get we can get a value of consequences of failure for every asset in our population. But of course, unless we provide specific information, we don't get that diversity, so you won't know which is more important. But you will be able to multiply that by the probability of failure to get your value of risk. So consequences. So we look at security of supply. So in CNAME, we call this network performance, and we can see that. So this is where I've bunched together the data points for the primary switchgear, and that's because for primary switchgear in the UK, we class these as assets where normally there would be a loss of supply to a customer in the event of the asset failing. So we look at the number of connected customers, we look at the customer sensitivity. So this is things like vulnerable customers. So in the UK, we have this duty of care to look at vulnerable customers. And then we also have a KVA band. And this gives us an idea of whether we're supplying sort of factories or hospitals or other types of asset where we need to include a multiplier. On the right-hand side, and they're generic for what we call LV and HV assets. So LV assets, I think of them as. HV is 6.6 and 11 kV in the UK. For assets that are at a higher voltage, so this is 33 kV and above, we take in the network type, which is whether it's secured network, whether or unsecure, so N or N-1, N-2, and we look at the maximum demand of the asset as well. That's generic, so that's why I've just added that to the slide. For safety, we look at the type, so this might be whether it contains oil or SF6 or something else. And then we also look at the location. So what we're trying to do with safety is understand how likely, in the event of the asset failure, is there to be somebody in the area that is impacted by that failure. So in a densely populated environment, there's more likely to be people around compared to a rural environment. And then we go on and look at environment. So these are the data points for the environment. So the type, again, does it contain oil or SF6? So obviously the leakage of those substances is undesirable. Proximity rating is the proximity to a watercourse, and that's relevant for oil assets if there's a chance of leakage. And then bunding is the oil containment system around the asset. So are we going to lose oil into the environment or SF6 into the environment? So that's what we do for environment. And then for financial, we're looking at, it's generic that we look at two things. So access financial rating is relating to whether that asset is immediately accessible or whether it's in, say, a building or underground or something like that. And that will have an impact on the cost. And then we look at the type, and the type is normally related to the size of the asset. So that's used for things like transformers. So different size transformers have different financial costs with regard to replacement if they fail. And so consequences of failure. So the consequences of failure is normally, not in every case, but it's normally dominated by the network performance or security of supply. There are some exceptions to that, but that's, for most assets, that's the usual case. And then of those, the maximum demand or number of customers, depending on which voltage you're at, is usually the most influential data point. So if you're going to collect anything and make sure you've got that, that's the thing that's going to influence the criticality of the asset more than any other data point. There is some variability based on the subcategory of the asset, so how large it is and what sort of insulator medium and things. So that information is usually known, so you can usually pick that up. And then there's other things which are usually easy to get hold of. So proximity rating, again, you can plot the coordinates and see how far from watercourses you are. That doesn't require specific information to go out and be collected. There might be some policy information. So if you know that all your assets are bunded, unless you know that they're not. So again, you can populate by exception there. For safety location, so in the UK, we have this ESQCR, so Electricity Safety Quality and Continuity Regulations, and that records land usage. But again, you could do that from a map and look at which are the rural ones and which are not, and then asset type. So for these consequence categories, they're usually quite easy to produce a data set for. It's not especially onerous collecting that particular information. So I realise we're sort of running short on time. So I've got a few slides on data quality. So I'm not going to actually go through these, but if you saw the previous data workshop, then I actually go through these in a little bit more detail on that one. But when you get your slides, and obviously if there's any questions, so there's a few little elements that we've suggested on data accuracy. So that's the collecting data. Timeliness, which is the important thing about the timeliness is that asset data degrades over time. So you collect it and you know it's true at that point of collection, but over time you're less confident because you know that time's elapsed and other things could have had it happen to the asset, and you can track that. And then also data completeness. And again, I've put an example of a sort of data completeness gathering plan on there. And then there's a few references. And then I apologise I've run over and talked too much, but please, if there's any questions, now's your opportunity. Felt
Thanks
a bit
very
rushed
much.
at the end, didn't it?
No, nicely done. There's a lot of information to squeeze in there, so thanks very much for that, Joanne. That's great. Just a comment from Vinoth in the chat there. Very difficult data set is cough off. We can calculate somehow. Obviously, there's previous webinars where we've touched on this, but do you have any comments on that, Joanne?
I think it's worth doing so even though it might be a bit manual, so hopefully I've gone through some of the data points which are more straightforward to collect for cough and giving you an idea of the data points that we would collect or the data points that are in CNAME. And it might not be practical to go through and look at all those assets on maps to work out their locations and things like that for high volume assets. But hopefully for lower volume assets, so your most important assets, your biggest switchgear transformers, it should be it should be practical, hopefully, to make some to get some indicator of which assets are more or less important. And again, using asset engineers couldn't be useful here because they will normally know, oh, these assets are the ones where we need to protect, and these assets are don't service too many customers. So you can use some of that heuristic, but any information is better than no information on that one. Did I see a hand up
Yep.
at some point as well?
Paul, I think you had your hand up. Do you have a question? Please do feel free to unmute yourself and fire away.
Yeah, hi, can you hear me?
Yes, we can, yeah.
Yeah.
I don't know if it's probably more just a question about what's been done in the UK. Is anyone using the CNAM modelling for trading assets off against each other in terms of looking at the overall risk profile of their assets, or is it not really designed that way? Is it more of a ranking and they're individually done in their own asset classes and not necessarily compared?
Yeah.
I just figure like it's an idea, but it would be very hard to actually get any accuracy. Is my thinking.
Yeah, there's certainly the profiles that come. So obviously with common methodology and with you produce risk, and risk is monetized, and so for every population of assets you've got that value of risk, and you could trade some for another. But there is, so when the network operators go through their business plans, they will look at the profiles of the assets and determine. So in the UK, we decide how much money we need to spend in each asset category, and then we produce a business case that goes to the regulator, and the regulator sort of says yes or no, or moderates that. So it all starts at the condition of the asset and what's required. So it's up to the network operators to think, oh well, we've spent X volume of X amount of money on this asset class, but we don't need that much going into the next price control, but we need more in, for a different asset class. And so they would have to make the business case that way. So they don't get a pot of money where they can sort of just trade, and as long as they deliver the risk reduction, that's okay. No, they do need to do it in the they need to do what they say they're going to do to deliver overall risk reduction. And it's quite tricky as well, because the biggest reductions in risk is by spending money on the highest value assets. That's where you'll get your most kind of bang for buck. And so you need to be careful to make sure that you're not compromising parts of your network by just going for the overall risk reduction. It has to be a sort of measured plan. So we do see some of that, but less. Yeah.
Okay, thanks very much.
That's your question, Will. Any other questions at this point?
It's all quiet, isn't it? So While it's all quiet, I'll just move on to the next slide. So if you want to know a bit more about what we do, I apologise for the slightly blatant sales pitch. So we help customers implement these kinds of methodologies within their organisations. Obviously, these webinars are free to attend, and we're going to continue doing those. But if you do want to know more about what we do and the systems that we've got, then do please give us a shout, and we'll be happy to have a conversation with you individually. And then in terms of the next webinar, so there's quite a lot of interest around CNAME, and so and especially using CNAME outside of its GB roots. And so we're sort of designed the next webinar on adapting British CNAME standard for non-UK utility asset owners or electrical asset owners. So that's going to be the subject of the next webinar. So that's on the 31st of May. So the 8 o'clock BST is the same time you've joined today, and then we do a later slot as well.
I don't think there's been any further questions in the chat.
Okay.
So yeah, just leaves us to wrap up then, and thank you very, very much for joining us, and thanks to Joanne, really informative, some great information there, and hopefully you found the session useful. Equally, just to mention, obviously, with future webinars, if there are any topics that you'd like us to explore in future sessions, by all means, please do throw in any suggestions, and we can look to pull those together. And equally, if you've got any questions after this session, please do get in touch. We look forward to hearing from you. And that, just thanks very much for joining, and take care. See you again for the next one.
Thanks everyone.
very much.
Thank you.
Thanks all. Bye now.
Bye.